My name is Kristin Williams. I'm an assistant professor at Emory University in the United States, and I'm presenting this work in collaboration with Emily Pondaven.
Hi everyone, I'm Emily. I'm a student at the University of St. Andrews. Excited to present to you all.
And even though you get both of us, we're actually representing a team of people who couldn't be here. And so that's my student, Sam Liu, who had wanted to be here, but hopefully is in the audience. So shout out, Sam, and Ari, Saikawa, and Jason, Jacques. And we're talking today about interacting with sensor data to understand uncertainty and air quality monitoring. Oh, arrows don't work either. This is fun.
Oh, maybe you can press there.
Oh, I got it. So visualizations are often used to communicate scientific data, and this has become really important recently as we all went through the COVID-19 global pandemic. And so we were all, glued to our monitors trying to understand the spread of the virus and how it might be affecting our day-to-day decisions. And so likewise, scientific data really is important for people's day-to-day decisions. And so the public communication of it becomes really increasingly important as we're making these more data-driven decisions and we're trying to communicate them out. So the definition of so data has uncertainty inherently baked within it. It enters it through many layers of the data collection process. So from measurement to processing to analysis and synthesis. And so you can't really get uncertainty out of your data. And what we mean by uncertainty is this working definition. So uncertainty is not a settled definition within the scientific community. And so we offer this characterization, and it comes from Jessica Holman and Scott Hudson's work, which the idea is that what we mean by uncertainty is that event as it is reported may not be characterized truly. And so when we sample the world and we have a sampled value, we recognize that the true value actually might be within a range of possible values. And the sample value is giving us evidence for that. And so we use the definition, the possibility that the observed value could take on a possible set of values. But in Jessica Holman's prior work, she found that even though we've got uncertainty baked into our data sets, a lot of times they are not, it is not communicated through data visualizations or other kind of data science applications. And she interviewed practitioners to understand why is that? And there were two main takeaways. One is that these practitioners believe that a visualization should communicate a very clear message. And second, that message should be derived from an independent process that establishes scientific confidence. And they believed that if they presented uncertainty within their visualizations, that would be obfuscating that message. And it was really important that that message be clear.
And I think adding on to that, I think especially with air quality today, it's often showed in the same way every single time, especially in the US, is showed with AQI colors to represent air quality within a map. And as a result, when you suddenly add this dimension of uncertainty, it might make it unfamiliar. And I think that's exactly what Jessica was saying from the study, that it might obscure that message, it might not show a clear message, but we're saying in reality, it's really important for scientific transparency.
Yeah, and Emily pulled this visualization from Purple Air, which is using low quality air sensors. And so you can see what she means by the AQI visualization. So the AQI is an air quality index developed by the Environmental Protection Agency in the US in consultation with scientists. And it uses this color coding scheme to send a message about whether the air is good quality or bad quality. So we were particularly interested in air quality sensors and the data that is collected by those sensors. They have problems with uncertainty in what is commonly known as sensor drift. So this can be because contaminants enter the sensor. This can be because of environmental changes, such as maybe there's weather fluctuations, or there could be mishandling of the sensor itself, say it drops, and so it becomes miscalibrated. So we focused on this point of capture of the data and our questions about uncertainty in air quality data. In our review of the literature, one of the things that stood out to us is that there are a host of techniques from the interaction design community for dealing with uncertainty. So particularly by involving the user or adding more context to data to make sense of it. And so in formulating our problem that we went after, we felt like there were a host of techniques we could be borrowing from interaction design to cope with uncertainty in air quality data. And so that really leads to our research question, which is how can interaction design help with communicating uncertainty in air quality data? And to answer this question, we, or more specifically Emily, generated 9 visualizations that encoded uncertainty, and we varied these along 2 primary dimensions. So one was their levels of interactivity, and the second was the context that was provided. And I'll get into the details about what I mean by levels of interactivity and context in further slides. We evaluated these visualizations using a crowdsourced study with 150 crowd workers. And the primary contributions of this work are one, the set of visualization techniques for communicating uncertainty in air quality data. And second, we have a bunch of findings talking about the principal role of interactive visualization design to support accurate, informed, and trustworthy scientific communication to inform better decision making. So we're going to talk about the design decisions and rationale for uncertainty encoding. We're going to talk about how the study design that we used in our crowdsourcing study. We'll also then turn to the findings about our trade-offs for understanding and decision-making with uncertainty, followed by the implications and what we really see as the future work that comes out of this research. So as I was saying earlier, we encoded uncertainty along 2 main dimensions, so interactivity level and context. And so what do we mean by context? So as Emily was saying, geospatial visualizations are the primary means of communicating air quality data. So we started with spatial context first. And then we delved into some of the assumptions of that to focus in on temporal context that might be shown in that visualization or the sensor itself. And so these were the 3 primary context types that we used.
And I also think it was interesting going into the context just because a lot of visualizations show map, it's difficult to show other aspects that are also important. So when you have a map, that often just represents air quality at a specific time, but you're able to show the different locations. What if you want to know at a specific location over time how both the uncertainty and the air quality changes, which is shown through the temporal visualizations? And what if you want to know the air quality at a specific location at a specific time and compare them super easily? And that allows us to do so through the sensor-only visualizations. And by dividing into different contexts, it allowed us to sort of see the differences between those.
So the second dimension that we varied was the level of interactivity. So what you just saw in this previous one is all static representations, but we started with the static representations, and then we also looked at adding a temporal level of interactivity. And particularly, we were drawing from previous work on hypothetical outcome plots. So the use of animated hypothetical outcome plots have been pioneered by Jessica Holman. And the idea with them is that if uncertainty is the possibility that the reported value could take on a range of values, then you use animation to step through the visualization of each of those values within that range. And so here we Emily innovates on Jessica's work by looking at this in the geospatial context, whereas Jessica had done it primarily in the error bar context. And then for our last condition, what we mean by interactivity is we gave the user the ability to control stepping through each frame of the animation by using a slider to control which frame they were interested in looking at.
And I think I think the ones that I'm most excited about is sort of the animation, the interactive, because I think uncertainty is often seen as something really complicated, and the hypothetical outcome plot, for example, in the animated one, sort of forces the user to see uncertainty without seeing as this like a dot and then the size is bigger because the uncertainty is bigger. Instead, by watching the animation for longer, it sort of ingrains that uncertainty in your brain and you're able to sort of see it over time instead of being able to ignore it. And that's really what we want to do through those visualizations.
So what data did we use to encode uncertainty? So we use data from the public website of the Environmental Protection Agency, and we particularly focused on California because they have a denser network of sensors than other states in the United States. And also the data coming out of Southern California allowed for a lot of fluctuation, so we could explore cases of not only good air quality, but also moderate to bad air quality. And we measured uncertainty by using root mean squared error. So the Environmental Protection Agency recommends you use the federal reference method or the federal equivalent method as the gold standard. This is the best way we could possibly measure air quality. And so the root mean squared error comes from comparing lower cost sensors or lower quality sensors to that gold standard. And so the root mean squared error is what is capturing that difference between the lower quality or lower cost sensor versus the gold standard. And we encoded that information in static representation using transparency and circled glyphs. And in the spatial context, and then in the temporal context, we encoded it using these polar bars. So the height of the polar bar represents the uncertainty, and we've got this dashed line to show what the EPA recommends as an acceptable or unacceptable level of uncertainty with the data. And then in the final one, it's the width of the needle. So even though we show these encodings all in static form right here, keep in mind that for the interactive one or the animated one, these are different. So particularly like the gauge style sensor, we have a moving needle in the animated context rather than the width of the needle. Yeah. So how did we evaluate this? Well, we crowdsourced our evaluation study. There's prior work to show that in-lab studies versus crowdsourced studies do comparatively well when it comes to visualization perception task. And so we thought it would be an appropriate approach to our questions. We didn't want to be accused of, hypothesizing after the fact. So we specifically developed a set of hypotheses about how we thought our uncertainty encodings might impact people's judgments. And so our first hypothesis is that we thought less animation would support more accurate interpretation of the air quality index. Our second hypothesis is we thought greater interactivity will support better understanding of uncertainty. And then our third is that we thought greater context will support more accurate and confident decision making. And so in our procedure, we did a couple of things like ask some background questions and do a training test, but I only want to focus on our measures because they help you understand how we evaluated these hypotheses. So our first measure was we asked a question about interpreting the air quality index for a location on the graph, and we measured the accuracy of that answer. The second is we asked participants to compare two locations on the visualization and decide which they thought was the more reliable data source. And then the third one is we asked them to self-report their confidence in their answers to the first two questions. So for our first hypothesis, despite our expectations, we saw that animated visualizations outperformed interactive designs. And notably, if you look at this bar graph, you can see that participants were much more likely to be inaccurate using our interactive visualization than they were to be accurate. And we found these results held up with a binomial regression using a logit linked function that had a significant difference. For our second hypothesis, we found support that there was greater interactivity did support better understanding of uncertainty, and we found that the three conditions were ordered in our expected order. Notably, participants were 1.7 times more likely using interactive visualizations than animated to understand which of the two locations was more reliable, and they were 2.1 times more likely using interactive visualizations compared to static visualizations. And again, this was backed by binomial regression using a logit linked function that this had a significant effect. For our third hypothesis that greater context would support more confident decision making, we did see a significant main effect. So our data was not normally distributed. We had to use an aligned rank transform, and after that, we used a repeated measures ANOVA. Subsequent paired t-test using the two-key adjustment method revealed that there was a significant difference between the map and sensor and a significant difference between the time and sensor. However, we caution you with reading too much into these results. So if you look at this graph, you can see there's a big peak in the bar here, and this is the animated sensor. And so we think a lot of those significant effects are being driven by this one condition. Because otherwise, the data kind of washes out across conditions. Some of the exploratory findings that we did not make any hypotheses about is that we saw that even though participants made incorrect responses during a training task, that just had no correlation between their confidence and their own judgments. We also found that slightly more than half of our participants could do only 2 of our 3 mathematical ability tasks. So we had a set of questions where people were asked to self-report their mathematical ability. These 3 questions were meant to capture a high school level of math proficiency. All of our participants had a college level except for 1, but they only reported being able to do 2 of these 3 tasks. And we also saw a moderate negative correlation between self-reported mathematical ability and correct responses. So the major takeaway that we found from these findings is that there's a trade-off between accurate air quality judgments and understanding the uncertainty with air quality data. So if you recall, participants were much more accurate using the static visualization than they were using the interactive visualization for making air quality or for interpreting the air quality index. But they also had a much better understanding of uncertainty in the interactive visualization than they did in the static visualization. So there seems to be a bit of a trade-off there between being accurate in your interpretation and understanding the uncertainty of that data. So what do we think some of the implications are future work that comes out of this? We think that future work should investigate interaction effects between levels of interactivity and confidence. And particularly, we note some really, we didn't see much differences in people's confidence across all of these conditions. So they're not really aware that they are making inaccurate judgments or that they understand uncertainty better. So we think there's some interaction effects going on that could be isolated and studied in future work. We also think that there's a lot of opportunity for interaction design to balance agency over seeing the full distribution of uncertainty in the data, but also making sure that the design encodes it in a way that people are sort of forced to reckon with aggregate trends so that they can be more accurate in their interpretation of the data. And lastly, we were using a spatial interpolation technique in our geospatial maps called kriging that is often used in these geospatial visualizations, and kriging had a bunch of challenges. So we particularly were asking participants to make a judgment about a spot in the visualization that could have been either good air quality, or it could have been moderate air quality. And the interpolation technique is making sort of judgments about how strong that is. But given the location of the sensors and their spatial sparsity, that kriging technique may be drawing inaccurate conclusions, and we don't have a way of knowing that. And so one thing we might keep in mind is how these algorithms are actually being designed for perception and decision making, and whether they're really well suited to that or not. I think Emily has some more to say about kriging, so I'm gonna.
Yeah. So I think whenever you're using kriging to interpolate the values on a map, there's a bunch of different parameters that you have to consider. And what we were trying to do is finding the most accurate one. You just don't want to use, there's something called a semi-variogram, which sort of decides sort of the method in which you interpolate between 2 different values. And because we were trying to find the most effective one, we were sort of experimenting with a bunch of different ones and used sort of it's like a computation where you leave one air quality sensor out, and then from the Kriging method, you would like predict that and then compare that to the actual value. We did that for every single air quality sensor and then found the one with the least amount of error. And sort of because our focus was more on looking at these set of visualizations and sort of figuring out what would produce the best like designs and how if like users were able to make accurate interpretations of the AQI and of the uncertainty, that was the main focus, but that's just something we noticed. And I think there's a lot of space for more research into finding better kriging techniques or other techniques, like other interpolation techniques, that would not have this error that we found.
Yeah, so there are a couple of limitations of our study. We only worked with 103 participants out of our 150, and you can see the paper for more about our filtering, but I'll just say we had some quality checks in our data that they didn't fail or they didn't pass, and that's how we filtered it. But the biggest limitation is that we're working with participants who all had a college level, and particularly we were running this study in the United States. Well, only 1/3 of the United States population has a college level degree. And even of our participants, you saw that their mathematical ability really wasn't being self-reported at the level that we would expect out of high school. So knowing whether these findings hold for a high school level equivalent of data literacy, I think will be very important for public communication. Um, so in conclusion, I hope you take this one big takeaway is that there's a real role here for interaction design to help with people understanding uncertainty. However, we have to be really careful with how this design helps people make informed and accurate judgments but also gives them the agency to understand how uncertainty might be impacting their day-to-day decision making. And we think there's tons of opportunity for future work to go down this path. Thank you.